Yes, thank you very much. So this is joint work with my colleagues Armando, Andre, and Franco. And it's on formal verification of confidentiality guarantees in a distributed social media platform. So the motivation is that on the web and on social media platforms in particular, users want to share information, sometimes publicly, but sometimes also privately with friends or family, for example. And for this purpose, the platforms provide privacy settings where the users can configure the visibility of the content. And this is then typically enforced using mechanisms like access control. But getting this enforcement right is notoriously hard. So a small bug in the implementation, for example, a missing access control check can easily lead to confidential data being leaked. So in this work, we wanted to follow a more rigorous approach and use information flow control. Capturing the confidentiality requirements as information flow properties and then formally verifying that there are no unintended flows of information in the system. And the system that we have looked at is a prototype of a distributed social media platform. And we had started developing this in previous work. For this paper, we have extended it to a distributed system. So you can now deploy the system on different servers, which can then communicate with each other. And this allows users to add friends also on other servers and exchange content with them on other servers. So this is similar to existing systems like Diaspora, for example. For the verification of the system, we have formulated and proved a compositionality result for a very expressive notion of information flow security. And we have formalized all of these results, so the verification of the system as well as the underlying theory in the interactive theorem prover Isabel Hall. And the code is available on the website. So let's look at the concrete system. We called it CoSMeDis. It offers the basic functionality that you would expect from a social media platform. So after logging in, you can browse content that has been posted by the users. You can add new posts with the title, text, image, and here you can also configure the visibility. Either it is a public post or it should be visible for your friends only. And you can manage friend lists, add friends both locally on the same server as well as remotely on other servers. So this is what the system looks like from a user perspective. Let's look at the architecture. So we have started by specifying the functionality of the system in the interactive theorem prover, Isabel. We use the Isabel's built-in functional programming language and essentially specified the step function of an automaton. So the actions here are the user actions, for example, create a new post or add a friend. And then the step function gives the output that is then displayed to the user. And the advantage of doing this in a theorem prover is that we can directly conduct a security proof on this specification on the one hand. On the other hand, Isabel also has a code generation feature that we have used to export this step function as executable Scala code. And this actually forms the core of the running prototype. And around it, we have built a wrapper that makes the actions and the outputs of this kernel available to a web application that we have built on top of it. So these outer layers, they are implemented manually, so they are trusted, but this kernel of the system corresponds quite directly to the specification that we have verified. So as I said, we wanted to map the confidentiality requirements to information flow properties. And the notion of information flow security that we have built upon is called bounded deducibility, or BD security. And it is a generalization of Sutherland's classical notion of non-deducibility. And here's a brief reminder of how it works. So we use trace-based semantics of the system. So we consider the behavior of a system in terms of its set of possible execution traces. We model the power of the attacker using an observation function O that maps a trace to the observation of the attacker. So this contains the information that the attacker can directly gain by observing or interacting with the system. And then we model what the confidential information is using a secret function S. So this extracts the confidential information out of a trace. And now the security requirement is that it must be possible to change this secret without changing the observation. So there must be a different possible trace of the system with a different secret, but the same observation. And this means that from the viewpoint of the attacker, this observation does not tell them which one of the secrets has actually occurred. And non-deducibility requires that it must be possible to change the secret in an arbitrary way, which is typically too strict for realistic systems, including our CoSMeDis. So BD security adds another parameter to this, called B, the declassification bound, where declassification means controlled information release. And it allows us to specify in a fine-grained manner which secrets have to be indistinguishable of each other. So this then allows us to specify essentially exceptions to this strict policy of non-deducibility. So we can, in other words, specify what the attacker is allowed to learn about the secret. So how have we used this for our system? We considered basically two classes of confidential information: the content of private posts that should be visible for the friends only, and the friendship relations between users. And we want to verify that, for example, the content of a friend-only post cannot flow to a user who is not supposed to learn about this because they are not friends with the owner. So the attackers that we consider here are users of the system, an arbitrary but fixed set of users, and the observations are therefore the actions that these users perform and the outputs that they get. So these are the green arrows here. And the secret is, for example, an update action to a post that we want to keep confidential. And now the security requirement is that whether or not this secret input has occurred, the observation must stay the same until the observers gain legitimate access to the secret. So for example, the owner of the post could decide to add one of the observers as a friend, and then they are allowed to learn about the content. Until the owner decides to remove the observer again as a friend, then everything that happens afterwards should be kept confidentially again. So we have quite dynamic bounds on the information release that we want to allow here in the system. And for details on how we formalized this, I refer both to this paper and also to the last year's paper at ITP, where we discussed this in more detail. The focus of the current paper is on how to verify these properties in a distributed setting. So as I said, we have extended the system so that it can be deployed on multiple servers that can communicate with each other. So we have added corresponding communication actions both to the system specification as well as to the wrappers in the outer layer. And for the verification, we have verified that the secret is still kept confidential in the presence of inter-server communication. So basically for each secret, a server can act in two roles, either sending a secret or receiving a secret. And we have verified that the confidentiality of both secrets generated locally as well as secrets received from other servers is preserved. And we have verified this on the level of individual instances of the system, and we have then used the compositionality results to lift this to a security property of the overall network. Now, the problem here is that information flow security is typically not compositional in general. So this is well known. This has already been observed in the 80s. And compositionality can fail, in particular if, for example, the security guarantee of one component relies on environment assumptions that are not satisfied by the other component. So as a small example here, you see two systems that exchange an observable message, and both of these systems individually are secure in the sense that it is possible to insert a secret message without changing the observation. But the problem is that the two systems do not agree on the communication protocol, so on the ordering of the secret or the observable message, which means that here synchronization fails, and we have an observable difference in the behavior depending on secret messages. So this composition is insecure. And there has been a lot of research on compositional notions of information flow security. And we have looked at the literature, but we have not found an existing framework that allowed us to compose these dynamic declassification policies that we had verified for our system. So we looked into the literature at existing frameworks and tried to adapt some of the insights there to come up with sufficient conditions for compositionality of BD security. So we make some assumptions. Some of these are straightforward. So we assume that the observations and secrets are compatible in a certain sense. For example, if the sending of a message is secret for one component, then it has to be secret also on the receiving end. So this is basically a prerequisite that the shapes of the security properties fit together. We also assume observable network traffic. So this means that we assume that all communication on a network is observable to some degree. Not necessarily the content, but at least the fact that communication happened. So this is similar in spirit to assuming a $V style network attacker who can inspect network traffic up to parts that are protected by encryption. And we made another simplifying assumption here that we call secret polarization, which means that any given individual item of confidential information, so for example, the content of a post, always originates in exactly one node of the network. And so this localization of the secrets, this helps avoid problems, subtle problems that might occur otherwise with where the scheduling of secrets may interfere with the scheduling of observations. And by having these assumptions, this allowed us to simplify our proofs considerably. So with these assumptions, we obtained compositionality results that allows us to compose security properties of a network of systems. The main strength of it is that it is policy agnostic in the sense that if these assumptions hold, then we can basically compose arbitrary policies. And intuitively, what the result is, if we consider a policy in terms of the amount of information that it allows to be released to the attacker, then basically this composition takes kind of the union of the amount of information. And this is allowed to be released to the attacker. So we combine the policies of the components. For CoSMeDis, we have chosen the policies so that they match each other, which means that our end result is that the security guarantees of the source node of a secret are preserved in the network. So if, for example, a user declares a post as friends only, then this setting is enforced throughout the network. Here you see some statistics of the verification. On the left side, you see the size of the verification of the monolithic, non-distributed version of the system. And on the right is the distributed one. And you can see that the size of the verification is roughly doubled when we added this distribution. And one of the main factors here is that we had to verify these two roles of each server, sending and receiving a secret. And we were able to reuse a lot of the proofs that we had done for the non-distributed system, but it was still a considerable effort to verify this distributed system. So it took us a few person months. So it was not automatic, but it was feasible. So to conclude, we had verified rich security properties for a prototype of a distributed social media platform, or at least the kernel of it and an abstraction of the network. But there's, of course, a lot of future work that might be interesting. For example, as I said, at the moment, the outer layer is trusted. Also, any client-side software, JavaScript, for example, that is running in the browser is trusted. So it might be interesting to look into how we can maybe extend our security guarantees here. There are also certain limits of code generation. So the code that is generated by Isabel is quite inefficient. So any improvements here on the efficiency of the code would be quite useful. And also relaxing the simplifying assumptions that we make, in particular the secret polarization, for example. It would be useful to allow our results to be applied to a more broader class of systems. So here's the homepage. As I said, the source code is available, so we can take a look at it. And this concludes my talk. Thank you for the attention.
Richard Navbelwa. First of all, I have a question about your diagram.
Mm-hmm. Which one?
The one with the comparison of the previous system and the new. Yes. Yes. What's the unit of measurement?
Pardon?
The left axis, unit of measurement, 25,000.
Right, it's lines of Isabel code, I forgot to mention.
Okay.
Yeah.
So verification is basically your proofs.
Yeah, verification here means the actual verification of the security properties of the concrete system. The security framework is the underlying theory. So in the distributed case, it includes the compositionality result and its abstract proof. And the system specification is the blue one. It also grew when adding the distribution features.
Okay, thank you. And the second question is, could you give an example of the dynamic declassification policies that you needed that weren't in the previous work?
Yeah, as I said, for example, here when we consider the confidentiality of a post, this is controlled by so if the user selects friends only, then this means that only friends should be allowed to be able to learn about the content of this post. But of course, the list of friends of the user evolves over time. So it might be that at some points of the execution history, the observer is a friend of the owner of this post and sometimes not, and this might change several times throughout the execution. And the properties that we have verified, they protect the confidentiality of anything that happens in phases where none of the observers is friends with the owner of the post, and at the point where an observer is added, the last version of the content is released basically to the observer. Anything that happens during phase of friendship is released. If the observer is deleted as a friend, anything that happens afterwards is kept confidential, and so on. So this is the kind of policy that we have formalized here.
Okay, let's thank Thomas and all the other speakers again.